Hi everyone, welcome back to BSc Chemistry Study Room. If you are new to this room, subscribe for more videos. And if you have already subscribed to this room, please click the notification button for more video updates. Thank you. In today's video, we are going to discuss or solve some problems under PB work, derive the first thermodynamic equation or formula, and do some certain example or problems solution under the formula. Here we go. Let's solve the example 1. Calculate the work done by an ideal gas when it expands from 1.0 liter to 2.0 liter against a constant external pressure of 1 atm. So the data given are here. V initial is from 1.0 liter. V final, it expands from 1.0 to 2.0 liter. That is the V final. Then the pressure given is 1 atm. By using work is equal to minus Vx dV. The reason why we put this negative sign is the work done is done by the environment, not by the system. Constant external pressure. It is an external pressure. The work is being loosed by the environment. So that is why we use W is equal to minus Px dV. Then we substitute these values inside this formula. W is equal to P pressure minus 1 atm. Then dV is V2 or V initial minus V final minus V initial. 2.0 liter minus 1.0 liter. It gives us 1.0 liter. Now, by multiplying minus 1 atm liter with 1 liter, we have W is equal to minus 1 atm liter. So work, the unit of work is in joule. We have to convert atm liter to joule. By the converting of atm liter to joule, we know that 1 atm liter is equivalent to 101.325 joule, and 1 atm liter minus 1 atm liter, the pressure given is equivalent to x joule. The numbers for the x we are going to find. Then now by cross multiplying, we have 1 atm liter times x joule. 1 atm times x joule is equal to minus 1 atm liter times 101.325 joule. After calculating the 1 atm liter times 101.325 joule, we have gotten minus 101.325 joule. By cross multiplying, in order to remove the liters, we have 1 atm liter divided by 1 atm liter. This liter cancel this liter. We remain with x joule. 1 atm liter minus 1 atm liter. We remain with minus 1 times 101.325 joule. So now x joule is equal to minus 101.325 joule. Therefore, our work done is equal to minus 101.325 joule. This means that the work has been done by the surrounding. The surrounding loses minus 101.325 joules. So that is it. Next question in example 2. Calculate the work done by an expansion of a cylinder from 0.7 liter to 5.2 liter against a pressure of 4 atm. The data given is V initial 0.7 liter to V final 5.2 liter and P external against a pressure external of 4 atm. So by using work is equal to minus Px dV and substituting these values inside this formula, we have work is equal to minus 4 atm into 5.2 liter minus 0.7 liter. we have work is equal to minus 4 atm, 5.2 liter minus 0.7 liter gives 4.5 liter. By multiplying, work is equal to minus 18 atm liter. So we are now converting atm liter to joule, since the unit of work done is in joule. So 1 atm liter is equivalent to 101.325 joule, and minus 18 atm liter, the liter we have gotten, is equivalent to x joule. By cross multiplying and dividing both sides by the atm, we have x is equal to minus 1823.85 joule. So therefore work is equal to minus 1823.85 joule. The work has been done by the surrounding. So that is why we have this value. So let's discuss on first law of thermodynamic. First law of thermodynamic. It assumes the law of conservation of energy, which states that energy can neither be created nor destroyed. Energy can neither be created but nor destroyed, but can be transformed from one form to another. So the energy is of two types: adiabatic and non-adiabatic work done. So for adiabatic, work for adiabatic is equal to du. Since we know dq is equal to 0, the heat supply is equal to 0. Adiabatic, as we discussed recent, is at constant heat supply. So dq is equal to 0. And for non-adiabatic, work for non-adiabatic is equal to du minus dq. So for infinitesimal change, du is equal to dw is equal to du minus dq. This small delta shows the infinitesimal change of the work done. So now, by making du subject of the formula, it will give us du is equal to dw plus dq. So now for measurable change of the internal energy, this u is the internal energy, du is the internal energy. So for measurable change of internal energy and path function of dw and dq, we have du measurable change is equal to w path function plus q path function, whereby du, change in u, is change in internal energy, w is the work done, and q is the heat supply. So here is the mathematical equation of first law of thermodynamic. Statements. There is a statement of thermodynamic which says the internal energy of an isolated system is constant, but the heat change is the difference between adiabatic and non-adiabatic work done. As we do, it is of two times adiabatic and non-adiabatic work done. So the difference is between the difference of adiabatic and non-adiabatic work done. So let's see some examples. Number one, calculate the internal energy of a system if 40 joule of heat energy is absorbed by the system and 60 of work is done on the system. The system absorbed 40 joule of heat and 60 work done is done on the system. So let's take this as the system. Here is the system and here is the surrounding. 60 work is done on the system. That means surrounding loses 60 of work to the system. That means the system gains 60 of work. That is positive 60. And 40 joule is absorbed to the system. This means the surrounding loses 40 of joule. When joule heat energy is loses, or is radiated from the surrounding to the system, we call the process as exothermic process. And when the system gained or absorbed the 40 joule of the heat, we call this process endothermic process. That means the system absorbed 40 joule of heat. So now, by using this formula, change in U is equal to W plus Q, work done, plus the quantity of heat supplied. Then du is equal to, since the system gained 60 work, so we are going to assign the 60 joule as positive, and it also gained 40 of heat, so we are going to still assign the 40 of heat as the positive sign. So we now get du is equal to 60 joule plus 40 joule, which gives us 100 joule. Example 2. What is the change in the internal energy of the system? The change in this system. If the surrounding gain 300 joule of heat and if 350 joule of work is done by the surrounding. So now let's assume this as the system and here as the surrounding. The question says the surrounding gain 300 joule of heat. That means the system loses 300 of heat minus 300 joule of heat to the surrounding. Now the surrounding gain 300 joule of heat. That is why the law stated that heat or energy can neither be created but nor destroyed, but can be transformed from one place to another. This shows us that energy from system transform from the system to surrounding, or in other words, it can be transformed from the surrounding to the system. So, and it says 350 joule of work is done by the system. Now the system loses 350 of work, and the system now consume or gain the 350 joule of work lost by the system. So now by using du is equal to W plus Q, du is equal to, by substituting the values, we have minus 350 of joule lost by the surrounding. That means the work lost by the surrounding, and plus 300 joule of heat, the heat gained by the surrounding. Therefore, the du is equal to minus 350 joule plus 300 joule. du is equal to minus 50 joule. This value tells us that the internal energy of the system is minus 50 joule. Example 3. The system releases 100 joule of heat energy. 200 joule of work is done by the system. Calculate the change in the internal energy of the system. So, let's assume this as the system again. The system releases 100 of joule of heat. 100 joule of heat is released by the system to the surrounding. Now the system loses 100 and the surrounding gain 100 of joule of heat. And again, the system done work of 200 joule. That means the system loses minus 200 joule of work and the surrounding gain 200 joule of work. So we are going to calculate the internal energy of the system. By using the formula, du is equal to W plus Q, and substituting these values of the system inside the formula, du is equal to W, the work loses by the system, minus 200 plus Q, the heat loses by the system, minus 100 joule. Now du is equal to minus 200 joule plus times minus 100 joule. du is equal to minus 200 joule minus 100 joule minus 300 joule. So this is the total internal energy of the system. So this is the last session of today's video. Don't forget to like, comment and subscribe to my BSc Chemistry study room. Thank you very much.